Welcome, colleagues. Welcome to SAMPE's Certification of Additive Manufacturing for Fracture Critical Applications webinar. It's going to be presented by Dr. Alison Park at NASA NESC. That's NASA Engineering and Safety Center. My name is Raj Manchand. I'm the SAMPE Chief Technology Officer, and on behalf of Alexandra Principe and Rocio Figueroa on the education team for SAMPE, we welcome you to this webinar. The SAMPE Space Applications Technical Leadership consists of Dan Polis, PhD of Sierra Space, and the Secretary is Jaden Pollock of University of Nebraska-Lincoln. We would like you to consider joining a SAMPE Technical Committee. The SAMPE Technical Committees are listed above. You can join any one of your choice on the 365 network. There will be some changes coming up to the technical committees that Dan will mention. The State of the Technology Industry Report is an industry resource developed by our technical committees. We urge you to download the complimentary copy on the SAMPE online store. Webinar sponsorship opportunities are available. We have a colleague at SAMPE, Jordan at sampe.org, who can let you know more if you're interested. Thank you so much. The Space Applications Group has put on many webinars this season. So this is a listing of the past webinars. The webinars are available on SAMPE YouTube channel and other media. Thank you so much. In the chat, please enter in your name, your title, your company name, and your geographic location. So again, in your chat, please enter in your name, your title, your company name, and your geographic location. It'll help us to get to introduce this more. Thank you so much. We have a large group today. So again, welcome to SAMPE's Space Applications Technical Committee webinar series. Certification of Additive Manufacturing for Fracture Critical Applications presented by Alison Park of NASA NEC. We're going to be starting momentarily. The Space Applications Technical Committee leadership is headed by Dan Polis of Sierra Space and Jaden Pollock of the University of Nebraska-Lincoln. Consider joining a SAMPE Technical Committee. It's a great opportunity to share knowledge, increase your professional network, and gain leadership experience. Above are the listed technical committees. The State of the Technology Industry Report was produced by the technical committees, and we welcome you to download your complimentary copy. Please do so on the SAMPE online store. Sponsorship opportunities are available. Please contact our colleague, Jordan at sampe.org. And finally, the Space Applications Group has put on numerous webinars this season, and they are all available on the store. I'm going to pass it over to you, Dan, for your moderation of this webinar. Thank you so much.
Thanks, Raj. Thanks, everybody, for joining. This is the last in our series of webinars. I really appreciate all the previous presenters from NASA, and it's a pleasure to have Alison Park here as our last speaker. Alison's the NESC Deputy Tech Fellow in Materials and Additive Manufacturing. For those of you not familiar with the NESC, that's based out of the Office of the Chief Engineer, and it's a great group that Alison's a part of. Alison's roles and responsibilities include working with the Tech Authority and program offices to qualify mission-critical AM hardware, and she's been instrumental in helping us do that exact thing. Prior to her assignment at NASA, she was the technical program manager at a leading rocket propulsion company responsible for capturing and managing R&D projects to mature AM technologies. She holds a BS in Materials Engineering from Purdue and an M in Material Science and MS in Aerospace Materials Engineering from UCLA. So with that, I'd like to introduce Alison Park, and I will get the charts up in a second, Alison. I guess two notes to viewers. First, I just want to note that we're recording this session, and it'll be available for re-review in a week or two. And also, if you could put your questions in the Q&A, that would really help, and we'll hit questions at the end. Let's make sure. Should be seeing the charts now.
Yep, excellent.
All right.
Thank you, Dan.
Awesome.
All right, let's go to the next chart. So again, nice to meet you all. My name is Allison, Deputy Tech Fellow at NASA Engineering and Safety Center. We're part of the NASA Chief Engineer's Office. So we handle all program under all mission directorates, especially in the area of materials, and I'm the focal for additive manufacturing. I'm responsible for safe implementation of AM hardware and design for critical NASA missions. Other way to say that is I am responsible for AM qualification certification, and I will go into a little bit of detail on the definition of it because everyone tend to have different interpretation of what AM qualification certification is. But my job is to make sure that our tech authority, i.e. Chief engineer for a certain mission, certain program, they understand the risk associated with this AM hardware. Is it just baseline risk? Is it elevated risk? Or is it reduced risk? So that they can literally sign the flight rational paper, right, in order to fly the hardware that's part of the system. So by design, that portion of my work is very high TRL driven, high TRL kind of world, right? We're dealing with very qualified state of material and manufacturing technology. We're dealing with very mature hardware that's literally ready to fly. But I also have eyes on the earlier TRL work, the AM technology innovation and maturation activities around the agency, as well as outside of the agency in the AM community. I value that very much because we have to do a really good job in order to get the R&D and get the AM tech maturation going in order to be on the good path for AM qualification. So I put a very important message on that. I am a big fan of sharing knowledge and talking to a lot of you. And I am very much on working together for rapid but safe implementation of AM technology. Let's go to the next chart, Dan. And I'm going to stop the video in case we have some issues. Okay, so I started my career 20-some years ago at the onset of Y2K, right? Late 90 and early 2000. And I work, and this is obviously way before I joined the agency. I work at a rocket propulsion company. I work alongside with actual engineers who worked on Apollo programs. But now, let's go to the next chart, Dan. Now we are called Artemis generation, right? The new mission that we are trying to go back to the moon and have a presence there. And let's go to the next chart, Dan. So it's an interesting thought exercise, right? What if the Apollo engineers that I work alongside, and they're very much expert in their field, they literally made the Apollo mission happen. What if they were exposed to AM technology? What would they have said, about what to watch for, or how to do it right? I think that they would say, "Hey, AM could have been big help for me, right? I don't have to wait for the design to mature, the design to be in the actual hardware, to test, to be able to say my design concept was right. With AM, I could do this very fast, especially in rocket propulsion area." But they will say, "Hey, the physics of rocket engine is still a challenge. We still have to overcome that. And we still need to know what to do that to overcome that," right? So they'll very much focus on importance in doing the groundwork, right? Getting processes control, know how your material is made, know what to define as a qualified material state, right? Know how to integrate to the rest of the system. So I think that message is very, very much, very much in our mind when we are trying to do AM implementation to critical missions. Let's go to the next chart, Dan. So as you guys already familiar with, we are not just playing in the low Earth paradigm, right? We are going beyond LEO, we're going into deep space area. Currently, as of today, a lot of AM, additively manufactured parts, are already being used for our program in very critical flight applications in all areas from Earth to deep space, right? In that human exploration area, right, human space flight, especially in deep space, we very much are on the thought process of it requires extreme reliability, and there is the importance of doing the AM qualification and flight certification right? So let's go to the next chart, Dan. So before we go to how we are doing that and what are the challenges of that, right? That is the theme of my presentation today. But let's get some definition on the same page, right? So the definition of qualification and certification. So the answer varies by industry, and even within the same industry, it varies by culture, right, within that entity. But the following interpretations are common that we use within NASA. So when we say qualification, AM qualification, we say those apply to parts, components, and then processes. When we say AM certification, we tend to use it as, hey, certification of design, subsystem, and eventually the integrated system. So certification by definition is granted by the responsible reviewing authority. So in the case of NASA, it is our tech authority, our chief engineers. When they have all the things on their plate, it says when the verification process is complete, and we're assuring that design, both AM design and both as-built AM hardware and all processed, will meet the established requirements to safely and reliably complete the intended mission. So that's how we use the definition of certification. Let's go to the next chart, Dan. So we've been qualifying the parts and certifying the flights for a long time, right? We've been in this business for a long time. So, and we also know how to integrate parts, however they're made, however they're manufactured, into complex system. We've been doing that for a while. So I say, hey, qualification is not that bad. It's not that hard. However, there are two elements, two tenets kind of go along with that, right? That kind of makes AM qualification is special, right? The first aspect is that individual nature of AM, right? Now you are the sole responsible party to make this material coming out of the printer to be sound and to be able to meet your mission, to your part performance. But you may not understand the potential failure modes on your standalone operation, or you may have, right, which is very good. So that process sensitive aspect of AM is what I think will make AM qualification a little bit special. Also, AM as of today, even though I myself in this AM journey for last 12, 13 years, but we still consider that this is a rapidly evolving technology. And that it comes with that, the fact that we literally just lack in experiences, and we don't know how to define that standard of excellence, right? What is excellent? What is good enough? What is good? What is bad, right? So if we play in that field, how do we manage how do we keep the balance between the blessing of AM, hey, we can do everything quicker and everything cheaper? How do we manage that with, still slow state of qualification and certification? Let's go to the next page, Dan. So here are some of the stuff that I from my vantage point, right? Now I wear the NASA hat, but I've also been on the other side of NASA being the customer for me. So here are some of the observations that I can list of current AM implementation that everyone's doing, especially in space, especially with metallic AM, especially in laser powder bed, right? I think we are very highly motivated to use this technology, which puts most complicated geometry, right? We want to be the best engineers. We want to produce, we're going for the grand slam, right? We want to put the most complicated geometry into the most critical parts of the system, right? Which is good, right? And we can do that with AM because we can do design, fail, fix, iteration so much quicker. But this puts the process, again, I'm going back to the individual local aspect of AM. I am solely responsible for my material, for my microstructure, for my structural integrity, right? So to that I say that there is more to AM alloys than bulk chemistry and tensile strength, right? Especially in the area of space, in the area of propulsion, launch vehicle. There are a lot of things that you need to worry about beyond the strength and ductility, right? And I list some of them here, and that's just, you know, a partial list of all the things a materials engineer worry about, right? But just like other traditionally made alloy systems, AM alloys are indeed complex, and it does require precise metallurgical control to meet the engineering expectation that you and your customer both set up and agreed upon, right? Against a variety of failure mechanism, right? That you know, material science 101, process, structure, property relationship. And also, again, I'm repeating myself here, that it's not just AM parts or AM material that you need to worry about. You need to be wearing a multidisciplinary hat, right? That your AM parts will be eventually and absolutely will be integrated into systems. So you need to look beyond that. Let's go to the next chart, Dan. So with that observation in mind, right, we, NASA, decided, okay, we need a set of governing policy. We need some set of standard that we need to put in place, not just for ourselves to be consistent and to give consistent advice or consistent feedback to whoever's implementing this, but for people who's going to bring AM hardware to us, right? So we formed a forum team, create the AM standard 60, 30, and 33. And we've been using this, actually. We've been actually citing this in programs and levying the requirements, either as written or as tailored, right? But today's presentation, I'm not going to go into detail on 60, 30, and 33. And so some of you are happy or some of you are sad about that. But what I'm going to tell you about 60, 30, and 33 is that even if you're not required to follow it, meaning you don't have a legit NASA program and you don't have a 60-30 levied on your program, even though you're not in that situation, it is really good read to kind of read through. In fact, I think you're in better place to read through this document and get a lot out of it if you don't have that requirement burden on you, right? It does have, I would say, up to 150 shall requirement listed, but underneath that, it has other rationale how we came up with that requirement. So that's all I have to say about that, because my presentation is not about this today, but I just want to set the tone that, yes, we have a standard that we follow, and this is going to help us with the topic that I'm going to be talking about. So let's go to the next topic, next page, I'm sorry. Let's go to the next one.
Are you seeing it, pyramid?
Yeah. Also, so I put this pyramid. This is, I'm hoping this kind of summarizes what 60-30 philosophy that 60-30 was based on. But it basically explains that you need to, first of all, you need to start this qualification process. You need to be on a mature engineering and production practice as a baseline, right? If you don't have that, maybe perhaps you're not ready for any AM qualification path, right? So once you have that, then you build a pyramid, right? Then you qualify your AM material as well as the process. the foundational state that you're going to define and verify. And then that comes along with the next block of pyramid, material properties suite, your design value as a reference distribution. And then along with the production, first pre-production article evaluation that you're going to be doing, as well as your part maturation, you're going to be inserting your statistical process control application. So I just want to put that out there, kind of summarize what the backbone philosophy of 60/30 was. Okay, so let's go to next chart. Okay, so this starts the meat of my presentation, right? So I do not know the maturity level of today's audience in terms of how NASA does things and what things that NASA calls and define. So this is more of like an intro chart for those of you who are not familiar with NASA speaks. And it could be a reminder if you're already in this space and do all this already, it's a good reminder. So we, NASA, put very much large importance on structural integrity, right? So I have an example. This is a notional rocket propulsion turboprop assembly. Let's say it does have multiple AM components in there. It could be the housing, it could be the rotors, it could be the stators. So both static and dynamic parts, right? Let's say that this will be a part of human-rated launch vehicle that we will procure, right? So we don't have design authority on this. Somebody's bringing this hardware in their own system for us to buy. Automatically, because it does have a human-rated launch vehicle description, it's going to be subject to our NASA AM standards, 60/30 and 33, right? It'll also be subjected to another standard that we've been using for a long time on fracture control standard. In that, you get to be classified into 3 different buckets: exempt, non-fracture critical, and fracture critical. So for those of you who are not familiar with definition of fracture critical, let's go to the next bullet point. So fracture critical is describes situation where a failure happens due to the presence of that known crack, and it's going to be catastrophic hazard, catastrophic failure, loss of mission, loss of crew. By being defined fracture critical comes with 2 assumptions. The first assumption is that your material and manufacturing processes, okay, they produce structure with cracks or flaws, right? We all material scientists know that none of the materials are perfect, right? It all comes with cracks and flaws, and compounded with different manufacturing processes, you're gonna have them, fact of life. The second assumption of being defined as fracture control is that the presence of cracks of sufficient size reduce the strength and life of your structure, right? So that's a working assumption. We also use a term called damage tolerance. Okay, for those of you who are not familiar with, damage tolerance describes situation, it's a situation that you have to demonstrate that a component can survive the service life with some safety factor in the presence of undetected flaws or damage, right? Again, being defined a damage tolerant, your part is damage tolerant, comes with three working assumptions. One is that components are manufactured from aerospace quality materials using control processes, right? ASTM or ASTM spec material, right? Second assumption is components are inspected or could be inspected for damage, right? And then third assumption is your component could be shown by either test or analysis or both to be tolerant to the undetected flaws. Let's go to the next chart. So again, I already said we've been using this concept of fracture control, the fracture critical part, damage tolerance. We've been doing all that for a long time for non-AM material, non-AM manufacturer processes, right? But when it comes to AM, additive manufacturing, especially metal AM, especially laser powder fusion, AM. Well, again, why so special when we talk about fracture critical components? So I made a little chart here, kind of distinguish between AM material versus non-AM, in this case, a raw material. So material quality in AM, material quality is highly process dependent. This is not a surprise to you, right? So the assumption is, and we do have verification and evidence of that it does vary. The material quality varies from machine to machine. In contrast, in raw materials, we are pretty confident. We've been working with this type of material for a long time. And we can say that raw materials are more consistent. They have more consistent quality due to a small number of dedicated production mills with extensive years, decades of experience. In the area of flaws, in AM material, I think we can say flaws are inherent to the process. It'll have flaws. It's a fact of life. And I'll go more detail about the definition of all this flaws and inherent flaws and process escape flaws. But in AM material, I think we need to, in addition to the naturally occurring flaws, we need to worry about the process escape flaws. And that actually puts a pretty important thing. But in raw materials, we just, a fact of life, right? Where flaws are typically rare because we believe the extensive activities the production mills did over the years. So we are confident the flaws will be rare. In the area of inspectability, AM materials, we could say inspectability varies based on the component geometry, right? We're not starting with a big chunk of material. We are making the material at the same time as part. And as I started the presentation, us engineers, we put the most complex geometry in the most critical area, going for the grand slam. So inspection techniques, so inspection in the way of non-destructive inspection, techniques are still under development to be able to kind of handle this complex geometry in the case of AM materials. In raw materials, right, you guys are already familiar with this. Raw stock is commonly fully inspectable. We've been doing this for a long time, and parts generally have very much high inspectability, and you know what to expect. Let's go to the next chart, Dan. So based on that, here are the challenges with highly complex AM components, right? So when I say highly complex AM components, I'm talking about parts like internally printed coolant channel, nozzle, or chamber, or the rocket injector that has many holes with rough surface finish, or still existing, and you cannot do the sound inspection. So I think I made it I hope I made it clear that in NASA's world, in NASA space world, ND inspections are very much foundational. That we believe that inspection, especially ND inspection, bounds the flaw size that might go undetected, right? We worry so much about the flaws and that might not be detected. So that's why we rely heavily on post-build ND inspection, right? Again, I told you about the definition of damage tolerant. We want to be in that state. We want to be damage tolerant, right? This simply means that we can fulfill the mission requirements, whatever the cycle or duty cycle requirements are. We are confident that we're gonna fulfill the mission requirements if we establish initial flaw size, right? In other words, if we know the largest flaw that an NDA, whatever the NDA technique you're gonna pick, might miss, we are gold mine. We're good. We're comfortable because we know this material will be damage tolerant. But the real problem right now, and we're literally facing every day, is that the types of AM hardware that users desire to produce are pretty complicated. Okay, so those are good. Those are a blessing of AM. We want them to push the technology and use to the full extent. But this this often leads to critical AM parts with very little or even no access for quantitative post-build surface volumetric NDE. So with the absence of reliable inspection, and we are supposed to rely on inspection to bound the initial flaw sizes, how does a traditional fracture control logic stand? The answer is it doesn't stand, right? So what is a new fracture control rationale logic that we need to come up with for this type of uninspectable fracture critical AM components? And then this is more important point. How do we communicate this, and how do we manage this associated risk with the person who's literally going to sign the certification of flight, right? So a group of us in NASA, starting about 2.5 years ago, we formed a team, and we first acknowledged that alternate approach is needed to come up with this fracture control rationale, right? And earlier the better, because we don't want to have this kind of discussion days before flight, right? We want this discussion to happen in the form of SMEs in the world of all the engineers that involve stakeholders, so that everyone knows what to expect. Everyone knows how to communicate, manage the risk. So we came up with one approach, and that's what I'm going to be showing you today. But to summarize, bottom line up front thing here, the last bullet is we are thinking about more from a risk-based acceptance rather than, hey, this part will survive X life with this critical initial flaw size that you can be detected with Y. Instead of that, because we can't do that right now with this type of AM hardware, we are going to go more with risk-based acceptance, right? We're thinking more in the context of distribution, in the flaw size, and how often they occur, right? We're also going to be using the concept of identifying and controlling the process escape flaws. We're also going to be using zone-based assessment. This part we might not worry about entire section of this part, but I do worry about this little local area that possibly not going to be inspectable. So I'll concentrate on that. So we'll use that concept. There are also concept of probabilistic damage tolerance analysis as well. Okay, so that's bottom line up front. So let's go to the next page, and I'll try to slowly go over this. This is not an easy concept for people to grab, even for myself, right? But the more we talk about it, the more we verbalize it, I think it makes it easier. So today I'm gonna try to do that for you guys. But let's define words again, right? So you've been noticing that I've been using flaws. I don't think I have used defects yet, but it's because I'm defining them differently, right? So flaws we define for the sake of this, alternate approach to fracture control, we are defining as imperfection or discontinuity that may be detectable by NDE, but it's not necessarily rejectable yet, right? So that's the definition of flaw that I'm using today. Defects, the dirty D word, is one or more flaws when they aggregate in size, shape, orientation, location. They do not meet specific acceptance criteria, and they are indeed rejectable. So that's the definition of defects for me. And then some people also use engineering cracks, especially when talking about linear elastic fraction mechanics area. But it's definitely defined as, we are defining as a flaw with sharp, flat interface that is large enough to be treated using continuum linear elastic fraction mechanics. Okay, so now we define the definition. Let's go to the next page. So group of group of us got together to start talking about this, but we all agreed on one thing, that we need to define the flaw state better for AM materials, right? And we decided, let's bucket them in two different buckets. And that's important because it helped us to kind of be rational about this this approach, right? So two buckets. So inherent flaws. We are defining the inherent flaws in AM material to be those flaws that are representative of characterized nominal operation of a qualified AM process, right? I'm going to say it again. Characterized nominal operation of a qualified AM process. So if you don't have a qualified AM process, qualified AM material, like let's not talk about inherent flaws. The assumption is you need to have a qualified AM process, and then you need to have the characterized nominal operation. You need to know what that process window is for you, for your AM process. The inherent flaws, we believe that they are expected to be common enough that a direct characterization is feasible. So what I mean by characterization implies that most inherent flaws have been observed as a part of AM process development. So when you first got the printer, you're trying to figure out the print parameter setting, the optimal one, you're going to define the process window. You are observing all those flaws and you know that they're to be expected. And you did include in the metallurgical and mechanical qualification data set, right? So it's already incorporated in your design because you already characterized it. You already tested that material that includes those inherent flaws. They are not defined by size. So example, small flaws does not necessarily mean it's inherent. But we expect it, and we've seen a lot of data. We expect to be small in very well controlled AM process. Very, again, this is just observation, but that's how we define inherent flaws. Okay, the second bucket, the process escape flaws. We define them as the flaws that are not representative of the characterized nominal operation of a qualified AM process. So it's opposite of inherent flaws. They are mostly associated with some sort of process failure. So if you look at the picture on the above, right, on the left side, I put the actual types of flaws, right? Porosity, lack of fusion, microcrack, unconsolidated powder particles. Those are names of the flaws. But in the area of defining process escape flaws, we're not calling it lack of fusion, right? We're calling it, it's more of concentrating on what caused that process escape flaws, what went wrong, right? They may or may not be larger than inherent flaws, though generally they're expected to be a larger. They definitely have lower occurrence rate, especially when you have your qualified AM process and you're confident in it, you should not have a large occurrence of process escape flaws. If you do, then you don't have a qualified AM process, right? The process escape flaws may or may not be detectable, right? And this is where we worry the most, that the case where they might not be detectable. Okay, let's go to the next chart. So group of us, we say, okay, let's figure out an approach where we can do this flaw state characterization. So we are using a distribution plot of flaw counts versus flaw sizes. So the fact of life here is that current metallic AM process do not produce perfectly dense material. They do have flaws. They might not be detrimental, but they have flaws, right? They generate some degree of porosity flaws, avoid even operating nominally. And we're okay with that. We're living with that, right? Fact two is, again, as mentioned before, process escape flaws are there, but they are rare, right? So I think with those two assumptions, we can put this notional flaw distribution plot, as you can see here. So we believe that by systematically defining and characterizing and controlling flaws that represent AM process. So by the way, saying this is easy, but actually doing this is a lot of work, as you can imagine, right? Characterizing these flaws to represent AM process, we think it's very important because we think it can be used as a foundation for developing this new logic, new fractal control rationale for uninspectable AM parts. We think that in order to characterize a process escape flaw distribution, again, it's not easy either, right? And one way of doing it, we think, is really spending a lot of time in thinking about potential failure modes associated with your AM process. So PFEMA come to mind that you may or may not be familiar with. Let's go to the next chart, Dan. So once you define this flaw state distribution chart, then your component specific assessment can begin. Okay, so if you see the plot, I already showed you the purple inherent flaw distribution plotted with the process escape flaw that's in green. So once you define that, now you go to your specific component and says, hey, what are my critical initial flaw sizes for this part? Again, the critical initial flaw size is defined as the smallest initial flaw that will cause component failure within the mission life with the appropriate factor of life, right? This is mathematical calculation using fraction mechanics, using strength properties and fracture properties, right? It's easily defined, right? For most of the AM part. So you can draw the line, the red line, where your local SIFS size exists in your flaw distribution plot. So that's step one. Step two that we're gonna do is let's see where the flaw detection capabilities, i.e. where is your ND detection capability exists on your distribution, flaw distribution plot. So those are blue lines that on blue vertical line that's on the plot, right? Again, the minimal detectable flaw size, the detectability of your ND technique is smallest flaw size that can be detected with ND with significant degree of reliability. So 90% of the time with 95% confidence. So let's go to the next chart. So if we can do that, this is, golden. We can do that, right? But again, my theme of my presentation is, and my worry, our challenge here is that some of the AM components, you don't know where the minimum detectable flaw size is because you just cannot use NDE. NDE is not possible. So inspectability challenge of AM. So this is a scenario, this is a plot that describes the exact scenario, right? The inspectable AM hardware situation, right? So in this case, your SIFs, your critical initial flaw size that you calculate using your properties and your linear fracture mechanics, it is larger than inherent flaw distribution, which is good news, right? Because you can say, hey, my design is incorporating my flaws are irrelevant in the sense of I don't need to worry about it anymore. It's already incorporated in my design, right? I design per this. But again, your blue line is, I notionally draw here, but sometimes you can't even draw here, right? Again, in uninspectable, you cannot use NDE. So once we make everyone aware of that, like, step one is acknowledgement, right? Like, this is where we are, right? And what is a possible approach to communicate this risk? Is this bad? Is this good? Is this good enough? So I listed the kind of thought process that we went through that could help us communicate the risk to appropriate tech authority, right? So first, we're gonna say, hey, inherent flaws, they're smaller than SIFs, so let's not worry about it. It's non-relevant, meaning it's already incorporated in your design, right? It's on your design curve. You design per that design curve, right? but rather let's focus our energy on the process escape flaws, the green lines in this plot, right? Let's focus on that instead, right? And instead of thinking, oh, what can we just get rid of this process escape flaws when and if we find it? Let's not think like that, but let's kind of shift that thinking to, hey, let's think about mitigation to limit the risk of process escape flaws, right? So this is where the rigorous PFEMA come to play to identify those potential process failures, right? You're going to be proactive on that to assess the risk of each process failure. So classic process control, where our 60/30 is very, very much strong on that. This is where it shines, right? Classic process control. It could be either in situ monitoring, in situ inspection, it could be machine health monitoring, it could be just classic statistical process control. The goal here is to control process failure and not necessarily to define and find and limit the process escape flaws. This is where we could introduce another new concept that NASA may not be familiar with because we're not doing this right now, but the concept of probabilistic damage tolerance calculation. At NASA right now, today, we're not using probabilistic damage tolerance approach. We are using deterministic approach more so. But probabilistic damage tolerance means that you are defining the probability of fracture rather than a defined service life, right? So you are going from accepting probability of failure, really risk-based acceptance rather than deterministic X life for X operation, right? And if you cannot accept this risk, then we tell the engineering group, hey, redesign or choose different manufacturing process. Perhaps AM was not a good choice for you for manufacturing process. Let's go to the next chart.
Hey, Allison, I'll just give you the 5-minute warning.
Okay, excellent. So as I mentioned, let's go to the next chart, Dan. Since I mentioned probabilistic risk versus deterministic life, I'll go over quickly on that. But basically, it does have both advantages and disadvantages, and we are working to how to incorporate this into coming up with a new fracture control rationale. So that's all I have to say since we're short on time. Let's go to next chart. So all in all, I am showing you what the smart people at NASA is thinking about how to deal with this. And by no means we're there. This is not ready for prime time. This is not ready to be codified into policy. We just start talking about it so that we know what kind of framework that we're going to be following, right? And what kind of framework that we're going to be discussing with people outside NASA like you guys. So I think this is very much a good opportunity, not just to come up with a new fracture control rationale, but this approach relies very heavily on understanding all potential flaw, right? Inherent as well as process escape flaws in AM parts. I think that it drives the user to pay more attention to flaw characterization. I myself have neglected in my AM journey, right? Because that's a lot of work, right? Especially during process development. But I think this kind of forced the users to pay more attention because at the end of the day, you have to, if we use this concept, you have to come up with a flaw state characterization and flaw description as well as flaw state distribution. I think it could accelerate the innovation in situ monitoring tools, advanced data analytics, and augment with the concept of ICME. I also think that PFEMA practice become more prevalent for AM. This is another area that we tend to kind of ignore. Oh, this is a quality person doing that. I don't need to worry about it. But it does provide a means to thoroughly assess your process, which I think is very, very crucial, right? And it provides a way to identify the potential process escape that would make you to have those flaws that's going to be undetectable. Users then can develop the rationale to mitigate the escape as identified from each failure mode. Let's go to the next chart, Dan. Yeah, so that comes to the end of my presentation. I understand this is not an easy concept. It's very much philosophical in a sense. So my apology if you're not expecting this kind of presentation, but I'm hoping that this generates conversation, especially in fracture and damage tolerance community, along with materials engineers and AM engineers. So thank you for this time. I really appreciate it. And I guess we'll take the questions.
Yeah, thanks, Allison. That was great. I really enjoyed it, and I love that NASA is thinking about probabilistic damage tolerance. So I really like that piece of it because we think about that here, and I think kind of risk acceptance and quantifying that's huge. So that was really interesting for me. Several questions here. So let's hit a few of them. Let's see. The first one is, can in situ monitoring technology be used to control non-traditionally inspectable areas?
Yes, very much so. So, I mean, I already put that in my chart, right? We're gonna be relying heavily on in situ monitoring, in situ inspection, right? But that has to come with the assumption, not assumption, but we need to be very much sure that those in situ inspection tools can do quantitative flaw detection, right? Or to be close to do that, right? At present, I don't think we are quite ready, but it doesn't mean that we're not gonna be relying on that partially, right? So I hope that answers the questions.
Yeah, thanks. The next one, how many samples are needed to show that all inherent flaws have been seen? I'm guessing maybe this means to establish your distribution.
Yeah, very good question. And again, that's the detail that we need to work through. I don't have an answer yet. I don't think anyone has. But whoever asked the question, do you want to be leading that effort? Contact me.
Let's see. This is one for, I think, in space. How do you check stability of parts made by additive manufacturing in a space environment? Are these flaw state characterization methods equally applicable for a space environment?
Yeah, so I probably should have started my presentation as this is, let's just worry about on Earth first and then deal with in space. But yeah, that's a very good question. I think eventually we absolutely need to think about that because we are literally, sending printers in space to do work, right? So yeah, the simple answer, but not quite 100% answer is yes, we'll be thinking about that.
Okay. This is the one I was thinking about. Considering the inherent challenges with the AM process, how much more difficult is it to qualify composites or other AM processes? I was thinking most of the methods that you laid out seem very applicable to composites, which is kind of the original additive process, right?
Yeah, I would say so, yes.
Right. Let's see. What is the biggest challenge for probabilistic fracture analysis, damage tolerance, gaining acceptance in the NASA fracture community?
Is this NASA person asking?
I know where he's from. He's from Sierra Space.
Okay. I would say, okay, so I've been, NASA's been my customer when I was on the other side, right? And we've been talking about this for a long time, right? Not just, on set of AM. So I would say now I'm on the AM NASA side. I think we are more open to it, right? And if probabilistic damage tolerance approach is gonna be one major player of this newly established fracture control rationale, we have to be open to it, right? But the disadvantage of probabilistic as you know, is it could be seen as less conservative, right? We NASA engineers love being conservative, right? And deterministic life is conservative, right? So that could be seen as disadvantage from like typical NASA engineering point of view, right? And then, I already talked about how, doing extensive characterization of flaw state distribution, like it requires a lot of work, right? And, how we're gonna do that to be determined. But we are currently working with major players like Southwest Research Institute, because they are using currently for aerospace, right? Aeronautics, right? So I'm sorry, aerospace, right? So yeah, I don't. To answer your question, I think we are very much interested. We are doing work.
So there's several more questions about kind of how you use probabilistic methods and orientation. I guess I'll maybe try to summarize into a question of mine. Are you using Monte Carlo methods where you're sampling from your distribution and basically putting them into the part in a random manner based on their occurrence rates to show, what's the rate of failure? Has NASA done any work there?
Yeah, so like mentioned, we are this is just one of the work. It's not just all the work, but we are working with Southwest Research Institute on their Darwin that they've been using. But Darwin was not made to be used with AM, right? There are some nuances that we have to work through in the workflow and even like philosophical approach. So we are doing that, but yeah, but at the end of the day, we want to ask the question, like, could probabilistic damage tolerance analysis provide a means of assessing the part risk in the absence of, that's the golden question, right? The details how to do that still in process.
Thank you. Let's see, has there been any work toward designing test artifacts that capture critical features to identify structural risks for a part with complex geometry? Let's see, I'm thinking in contrast to machine witness coupons that are limited to fully dense ASTM or similar test geometry. So I'm guessing more like, element test, you advocate for element testing that are related to capture some of the complex geometries.
Yeah, so I tend to loop all that in the classic process control, right? And our 6030 really encourage that. We actually force you to think about what kind of process control you're going to do. So that can be one of the way.
Great. There's actually still several more questions. I think I do want to, several people asked just on the logistics of getting charged. So we actually, as we said at the beginning of the talk, we recorded this talk. It'll be available on SAMPE 365 within a week or two. So if you want to see this presentation, you can see it there. I think I want to make sure I respect everybody's time. So sorry I couldn't get to everybody's questions today. Allison, thank you so much for kind of ending this webinar series for the TC7 Space Applications TC. It was great. And everybody look for, I guess, a future reorganization where we'll be setting up a new TC for materials in extreme environments. So thank you so much. And yeah, hope to see you the next time we have a webinar. Bye-bye.